In cryptography, a zero-knowledge proof or zero-knowledge protocol is a method by which one party can prove to another party that a given statement is true, without conveying any information apart from the fact that the statement is indeed true. If proving the statement requires knowledge of some secret information on the part of the prover, the definition implies that the verifier will not be able to prove the statement in turn to anyone else, since the verifier does not possess the secret information. Notice that the statement being proved must include the assertion that the prover has such knowledge. If the statement consists only of the fact that the prover possesses the secret information, it is a special case known as zero-knowledge proof of knowledge, and it nicely illustrates the essence of the notion of zero-knowledge proofs. Proving that one has knowledge of certain information is trivial if one is allowed to simply reveal that information. The challenge is proving that one has such knowledge without revealing the secret information or anything else. For zero-knowledge proofs of knowledge, the protocol must necessarily require interactive input from the verifier, usually in the form of a challenge or challenges such that the responses from the prover will convince the verifier if and only if the statement is true. This is clearly the case, since otherwise the verifier could record the execution of the protocol and replay it to someone else. If this were accepted by the new party as proof that the replaying party knows the secret information, then the new party's acceptance is either justified, the replayer does know the secret information, which means that the protocol leaks knowledge, and is not zero-knowledge, or it is spurious, i.e., leads to a party accepting someone's proof of knowledge who does not actually possess it. Some forms of non-interactive zero-knowledge proofs of knowledge exist, but the validity of the proof relies on computational assumptions. Abstract example. There is a well-known story presenting the fundamental ideas of zero-knowledge proofs, first published by Jean-Jacques Quisquater and others in their paper, How to Explain Zero-Knowledge Protocols to Your Children. It is common practice to label the two parties in a zero-knowledge proof as Peggy and Victor. In this story, Peggy has uncovered the secret word used to open a magic door in a cave. The cave is shaped like a ring, with the entrance on one side and the magic door blocking the opposite side. Victor wants to know whether Peggy knows the secret word, but Peggy, being a very private person, does not want to reveal the fact of her knowledge to the world in general. They label the left and right paths from the entrance A and B. First, Victor waits outside the cave as Peggy goes in. Peggy takes either path A or B. Victor is not allowed to see which path she takes. Then, Victor enters the cave and shouts the name of the path he wants her to use to return, either A or B, chosen at random. Providing she really does know the magic word, this is easy. She opens the door, if necessary, and returns along the desired path. However, suppose she did not know the word. Then, she would only be able to return by the named path if Victor were to give the name of the same path by which she had entered. Since Victor would choose A or B at random, she would have a 50% chance of guessing correctly. If they were to repeat this trick many times, say 20 times in a row, her chance of successfully anticipating all of Victor's requests would become vanishingly small. Thus, if Peggy repeatedly appears at the exit Victor names, he can conclude that it is very probable, astronomically probable, that Peggy does in fact know the secret word. One side note with respect to third-party observers. Even if Victor is wearing a hidden camera that records the whole transaction, the only thing the camera will record is in one case Victor shouting A and Peggy appearing at A, or in the other case Victor shouting B and Peggy appearing at B. A recording of this type would be trivial for any two people to fake. Such a recording will certainly never be convincing to anyone but the original participants. In fact, even a person who was present as an observer at the original experiment would be unconvinced, since Victor and Peggy might have orchestrated the whole experiment from start to finish. Further, notice that if Victor chooses his A's and B's by flipping a coin on camera, this protocol loses its zero-knowledge property. The on-camera coin flip would probably be convincing to any person watching the recording later. However, digital cryptography generally flips coins by relying on a pseudo-random number generator, which is akin to a coin with a fixed pattern of heads and tails known only to the coin's owner. If Victor's coin behaved this way, then again it would be possible for Victor and Peggy to have faked the experiment. Definition: a zero-knowledge proof must satisfy three properties. Completeness: if the statement is true, the honest verifier will be convinced of this fact by an honest prover. Soundness: if the statement is false, no cheating prover can convince the honest verifier that it is true, except with some small probability. Zero knowledge: if the statement is true, no cheating verifier learns anything other than this fact. This is formalized by showing that every cheating verifier has some simulator that, given only the statement to be proved, can produce a transcript that looks like an interaction between the honest prover and the cheating verifier. The first two of these are properties of more general interactive proof systems. The third is what makes the proof zero-knowledge. Zero-knowledge proofs are not proofs in the mathematical sense of the term because there is some small probability, the soundness error, that a cheating prover will be able to convince the verifier of a false statement. In other words, zero-knowledge proofs are probabilistic proofs rather than deterministic proofs. However, there are techniques to decrease the soundness error to negligibly small values. A formal definition of zero-knowledge has to use some computational model, the most common one being that of a Turing machine. Let and be Turing machines. An interactive proof system with for a language is zero-knowledge if for any probabilistic polynomial time verifier there exists an expected PPT simulator such that the prover is modeled as having unlimited computation power. Intuitively, the definition states that an interactive proof system is zero-knowledge if for any verifier there exists an efficient simulator that can reproduce the conversation between and on any given input. The auxiliary string in the definition plays the role of prior knowledge. The definition implies that cannot use any prior knowledge string to mine information out of its conversation with, because we demand that if is also given this prior knowledge, then it can reproduce the conversation between and just as before. The definition given is that of perfect zero knowledge. Computational zero-knowledge is obtained by requiring that the views of the verifier and the simulator are only computationally indistinguishable, given the auxiliary string. Practical examples: discrete log of a given value. We can extend these ideas to a more realistic cryptography application. Peggy wants to prove to Victor that she knows the discrete log of a given value in a given group. For example, given the value, a large prime and a generator, she wants to prove that she knows a value such that, without revealing, this could be used as a proof of identity, in that Peggy could have such knowledge because she chose a random value that she didn't reveal to anyone. Computed and distributed the value of to all potential verifiers, such that at a later time, proving knowledge of is equivalent to proving identity as Peggy. The protocol proceeds as follows. In each round, Peggy generates a random number, computes and discloses this to Victor. After receiving, Victor randomly issues one of the following two requests. He either requests that Peggy discloses the value of, or the value of. With either answer, Peggy is only disclosing a random value, so no information is disclosed by a correct execution of one round of the protocol. Victor can verify either answer. If he requested, he can then compute and verify that it matches. If he requested, he can verify that is consistent with this by computing and verifying that it matches. If Peggy indeed knows the value of, she can respond to either one of Victor's possible challenges. If Peggy knew or could guess which challenge Victor is going to issue, then she could easily cheat and convince Victor that she knows when she does not. If she knows that Victor is going to request, then she proceeds normally. she picks, computes and discloses to Victor, she will be able to respond to Victor's challenge. On the other hand, if she knows that Victor will request, then she picks a random value, computes, and discloses to Victor as the value of that he is expecting. When Victor challenges her to reveal, she reveals, for which Victor will verify consistency, since he will in turn compute which matches, since Peggy multiplied by the inversive. However, if in either one of the above scenarios Victor issues a challenge other than the one she was expecting and for which she manufactured the result, then she will be unable to respond to the challenge under the assumption of infeasibility of solving the discrete log for this group. If she picked and disclosed, then she will be unable to produce a valid that would pass Victor's verification, given that she does not know. And if she picked a value that poses is, then she would have to respond with the discrete log of the value that she disclosed, a value that she obtained through arithmetic with known values, and not by computing a power with a known exponent. Thus, a cheating prover has a 0.5 probability of successfully cheating in one round. By executing a large enough number of rounds, the probability of a cheating prover succeeding can be made arbitrarily low. Hamiltonian cycle for a large graph. The following scheme is due to Manuel Bloom. In this scenario, Peggy knows the Hamiltonian cycle for a large graph. Victor knows G but not the cycle. Finding a Hamiltonian cycle given a large graph is believed to be computationally infeasible, since its corresponding decision version is known to be NP-complete. Peggy will prove that she knows the cycle without simply revealing it. To show that Peggy knows this Hamiltonian cycle, she and Victor play several rounds of a game. At the beginning of each round, Peggy creates a graph which is isomorphic to G. Since it is trivial to translate a Hamiltonian cycle between isomorphic graphs with known isomorphism, if Peggy knows the Hamiltonian cycle for G, she also must know one for H. Peggy commits to H. She could do so by using a cryptographic commitment scheme. Alternatively, she could number the vertices of H. Then for each edge of H write a small piece of paper containing the two vertices of the edge and then put these pieces of paper upside down on the table. The purpose of this commitment is that Peggy is not able to change H while at the same time Victor has no information about H. Victor then randomly chooses one of two questions to ask Peggy. He can either ask her to show the isomorphism between H and G, or he can ask her to show a Hamiltonian cycle in H. Victor can verify that they are indeed isomorphic. If Peggy is asked to prove that she knows the Hamiltonian cycle in H, she translates her Hamiltonian cycle in G onto H and only uncovers the edges on the Hamiltonian cycle. This is enough for Victor to check that H does indeed contain a Hamiltonian cycle. Completeness. If Peggy does know a Hamiltonian cycle in G, she can easily satisfy Victor's demand for either the graph isomorphism producing H from G or a Hamiltonian cycle in H. Zero knowledge. Peggy's answers do not reveal the original Hamiltonian cycle in G. Each round, Victor will learn only H's isomorphism to G or a Hamiltonian cycle in H. He would need both answers for a single H to discover the cycle in G. So the information remains unknown as long as Peggy can generate a distinct H every round. If Peggy does not know of a Hamiltonian cycle in G, but somehow knew in advance what Victor would ask to see each round, then she could cheat. For example, if Peggy knew ahead of time that Victor would ask to see the Hamiltonian cycle in H, then she could generate a Hamiltonian cycle for an unrelated graph. Similarly, if Peggy knew in advance that Victor would ask to see the isomorphism, then she could simply generate an isomorphic graph H. Victor could simulate the protocol by himself because he knows what he will ask to see. Therefore, Victor gains no information about the Hamiltonian cycle in G from the information revealed in each round. soundness. If Peggy does not know the information, she can guess which question Victor will ask and generate either a graph isomorphic to G or a Hamiltonian cycle for an unrelated graph. But since she does not know a Hamiltonian cycle for G, she cannot do both. With this guesswork, her chance of fooling Victor is 2 minus n, where n is the number of rounds. For all realistic purposes, it is infeasibly difficult to defeat his zero-knowledge proof with a reasonable number of rounds in this way. Variants of zero-knowledge. Different variants of zero-knowledge can be defined by formalizing the intuitive concept of what is meant by the output of the simulator, looking like the execution of the real proof protocol in the following ways. We speak of perfect zero-knowledge if the distributions produced by the simulator and the proof protocol are distributed exactly the same. This is, for instance, the case in the first example above. Statistical zero-knowledge means that the distributions are not necessarily exactly the same, but they are statistically close, meaning that their statistical difference is a negligible function. We speak of computational zero-knowledge if no efficient algorithm can distinguish the two distributions. Applications. Research in zero-knowledge proofs has been motivated by authentication systems where one party wants to prove its identity to a second party via some secret information but doesn't want the second party to learn anything about this secret. This is called a zero-knowledge proof of knowledge. However, a password is typically too small or insufficiently random to be used in many schemes for zero-knowledge proofs of knowledge. A zero-knowledge password proof is a special kind of zero-knowledge proof of knowledge that addresses the limited size of passwords. One of the most fascinating uses of zero-knowledge proofs within cryptographic protocols is to enforce honest behavior while maintaining privacy. Roughly, the idea is to force a user to prove, using a zero-knowledge proof, that its behavior is correct according to the protocol. Because of soundness, we know that the user must really act honestly in order to be able to provide a valid proof. Because of zero-knowledge, we know that the user does not compromise the privacy of its secrets in the process of providing the proof. This application of zero-knowledge proofs was first used in the groundbreaking paper of Oded Goldreich, Silvio Micala, and Avi Wigderson on secure multi-party computation. Challenge is proving that one has such knowledge without revealing the secret information or anything else. For zero-knowledge proofs of knowledge, the protocol must necessarily require interactive input from the verifier, usually in the form of a challenge or challenges such that the responses from the prover will convince the verifier if and only if the statement is true. This is clearly the case, since otherwise the verifier could record the execution of the protocol and replay. In cryptography, a zero-knowledge proof or zero-knowledge protocol is a method by which one party can prove to another party that a given statement is true, without conveying any information apart from the fact that the statement is indeed true. If proving the statement requires knowledge of some secret information on the part of the prover, the definition implies that the verifier will not be able to prove the statement in turn to anyone else. Since the verifier does not have knowledge exist, but the validity of the proof relies on computational assumptions. Abstract example. There is a well-known story presenting the fundamental ideas of zero-knowledge proofs, first published by Jean-Jacques Quisquater and others in their paper, How to Explain Zero-Knowledge Protocols to Your Children. It is common practice to label the two parties in a zero-knowledge proof as Peggy and Victor. In this story, Peggy has uncovered the secret to someone else. If this were accepted by the new party as proof that the replaying party knows the secret information, then the new party's acceptance is either justified, the replayer does know the secret information, which means that the protocol leaks knowledge, and is not zero-knowledge, or it is spurious, i.e., leads to a party accepting someone's proof of knowledge who does not actually possess it. Some forms of non-interactive zero-knowledge proofs not possess the secret information. Notice that the statement being proved must include the assertion that the prover has such knowledge. If the statement consists only of the fact that the prover possesses the secret information, it is a special case known as zero-knowledge proof of knowledge, and it nicely illustrates the essence of the notion of zero-knowledge proofs. Proving that one has knowledge of certain information is trivial if one is allowed to simply reveal that information. The